All right, so before we start, let me mention we need to have some announcement. Let's see. So midterm coming up next Thursday. Time flies. We just give you back your midterm 1, but midterm 2 next Thursday. You know the drill, same thing as midterm 1. So in class and closed book, and you can have 2-page notes. You can reuse the page you have last time for materials in the before midterm 1, or you can make 2 new pages, whatever you like. 2-page notes allowed, okay? And again, calculator, we try not to have you, not to turn this into just a competition of your calculator skills, but some number crunching is still unavoidable. The screen is not showing, and okay, plug this in, that should help. Let's see. Yes, okay, all right. Okay, and what does it cover? So it covers topics cover up to Thursday, up to this Thursday. So the lecture today and the lecture next time. So to this Thursday's lecture. And roughly 4 problems you can anticipate. We'll try to reduce the number of subproblems. So last time there are many subproblems. So we try to reduce that to a more reasonable number. So you will have hopefully more time to work on the problem rather than rushing through it. Okay. Any questions on it? Yep.
Is it going to be cumulative, or is it going to be cumulative or from like midterm?
It will be primarily focused on the topics after midterm 1 because there's so much new materials covered, and but you know it's not going to be like totally independent of topics covered before midterm 1. For example, if we ask junction capacitance, junction is present in MOS, so it's still within range. But primarily topics in between midterm 1 and 2. Okay? Yes?
Do we have new homework this week?
New homework this week? Yes, there will be new homework this week. It's supposed to help you prepare, but we may have to figure out when it's due and when to give you solutions and so on. Okay, and we'll post a simple midterm. Okay. This week. Okay. All right. So we talked about the transistors last time. So I like to spend some time review what we have talked about. If this is the first time, which for most of you, this is the first time you encounter any transistor or 3-terminal devices, it will take a little bit to think about it for all the concepts to sink in. So today I'm going to kind of focus on from the model point of view. Okay. Last time we start from the physics. This time we'll start from a model. Okay. So we say, well, the transistor is well known to have this family of curves, okay, and this defined in the plane of I ID, the drain current, or IDS, versus VDS, okay? And there are two regimes divided by this parabolic line. And in here, we call this a saturation regime, okay? And in saturation regime, IDS is equal to 1/2 Kn times V overdrive square. Okay, very simple characteristics. V overdrive is equal to VGS minus VTN. Okay, and let me draw the transistor here. This is really for NMOS. Okay, and so here is VGS. Okay. And here is VDS, and the current ID or IDS will be equal to the current flowing through the source because the gate is insulating, okay? And we're following a symbol where this stands for the total voltage. So this really includes DC plus AC signal. Pure DC signal, we will use VGS, okay. Pure AC signal, we'll use small v, small g, small s. So K's matter here in the notation. This is being followed by most textbooks and data sheets and papers and so on. So this is kind of commonly accepted. And on this side, this is what we call a triad region. The name stems from vacuum tubes. I will not bore you with physics of vacuum tubes. So in the triad region, IDS is kind of a little bit different. It's Kn and VOV, overdrive voltage, VDS minus 1/2 VDS square. So it's a parabolic curve, okay? Now for those of you who are not familiar with, who forgot about your algebra, so let's look at this curve in more detail. So this curve, it's a negative sign, second order polynomial. So it's a parabolic curve, okay? And the parabolic curve passing through 0, 0. So we know VDS equals 0. Well, IDS equals 0. So it passed through the origin here. This is IDS. This is VDS. Okay. And we also know that you can substitute that in there. If VDS is equal to 2 times V overdrive, IDS is equal to basically 2 VDS square minus 2 VDS square, okay, times Kn. And so this is still equal to 0. So it is equal to 0 here. And we can also find out the maximum value. So if we take a derivative dIDS, dVDS, setting the derivative equal to 0, and this is equal to Kn, all right? The first term is just V overdrive. The second term become VDS, okay? So the maximum occurs when VDS is equal to V overdrive, okay? So somewhere in the middle, this term is going to be equal to 0. And when they are equal to 0, IDS at this time, maximum value is equal to, if you substitute VDS into the equation of IDS equal Kn V overdrive V ds minus 1/2 V ds squared. So you get exactly 1/2 Kn V overdrive squared. So that's this value here. So it's a parabolic curve, okay? And this value here is 1/2 Kn V overdrive squared. The vertical the maximum value occurs when VDS equal to V overdrive. All right, so that's the parabolic curve. This is exactly the parabolic curve, the first part of the parabolic curve here. And then we argue that, well, the current actually will not decrease. Mathematically, now this is just an equation. Equation is not physics. Equation is a model we use to describe the physics. So this part, the second part of this curve is actually not physical, okay? This is not physical because it did not consider the case of pinching off. So at this point, now we say, well, it should be just equal to the constant, as in this part of the curve here, where it should be just a constant. So what happened here? Well, the channel starts to pinch off, okay? So the channel so let's reproduce the curve here. So there are really two parts of the curve. The first part, parabolic part, okay, and then there is this just constant part. Initially, in this part, if we look at the device cross-section, this is a MOS. It has two N+ terminal. So this is source, this is drain, this is gate, and the substrate is a P-type silicon, all right? In this part, the electrons are basically populating over the entire channel. There's still more electrons near the source because there's a channel potential. So if you think about the channel potential, you think about the potential along this channel here. So this channel potential, if we say, you know, here is x equal to 0, here is x equal to L, and this channel potential, V of x, should be equal to Vs when x equals 0, and Vx should be equal to Vd when x equal the channel length. Now, at the pinch-off point, so when Vds is equal to V overdrive, okay, that's the pinch-off point. At this pinch-off point, the charge here, the Q, when x equal to L, is equal to capacitance per unit area, okay, times VGS minus the local channel potential here, okay. So this should be really V channel potential, x equal to L, and minus VTN. So that's the excess charge, inversion layer charge. So if this is equal to V overdrive, then we'll say, well, okay, the charge here becomes 0. So at this point, the charge becomes 0. Okay. So if we reproduce the plot, at this point, the charge density just become 0 here. So this is the electron density. So at here, locally, the charge just started to become 0. And this allows us to continue to increase VDS without changing current. So these allow us to progress to the point. If I draw the next part, okay, if we further increase VDS, what happens is the charge is going to become shortened. So in this area, there's no charge at all, okay? So this is this part. Okay. So that's the IV curve. Mathematically, both the mathematical model, okay? So you know this first part of the parabolic curve, and right at the maximum, we truncate the second half of the parabolic curve, and we just substitute it with kind of a physical argument, physical intuition. The current at that point should not change anymore. The same number of electrons is injected from the source, so the current should stay the same, okay? Later, towards the end, we'll see it's not exactly constant. There's actually a slight variation. But for now, this is the picture here. Yep? The channel, so the channel here, there's no electrons here. So it looks like the channel is interrupted. It looks like there's no charge to respond to current. However, in the transistor, the charge is being injected from the source. So even though it doesn't have electrons, but there are plenty of electrons to the left. This electron will continue to be accelerated through the high field region where there's no charge. This is like I describe it as like a waterfall. So initially there's a slow, gentle slope. River is coming down with lots of water, and then you go through a waterfall where it drops a lot of voltage, and the water just dropping down. So there's no kind of accumulation, steady state charge, but there are a lot of charges flying by. Yes?
If we connected the body to the source,
yeah, right. Body, so we have not talked about body. Indeed, the transistor is a 4-terminal device. The substrate is connected to B, body. And normally for NMOS, we will say, well, we connect the source to body. And that will be the normal operation. Sometimes we will actually intentionally change the body bias. So we could put a separate contact to the body and intentionally applying a different voltage. And when do we do that? Actually, the threshold voltage depends on the body bias. So sometimes we want to completely shut off one block of a circuit, as in many of the low power circuit, which is quite popular now. We will shift the threshold voltage of an entire block of circuits. We will change their body bias. So it is being used as an additional knob to tune the circuits. For most of our lecture materials, we will assume they are tied to the source. Okay. Questions? Any more questions? So this summarizes what we have learned for last Thursday's lecture. Okay, so 2 simple equations. Let's do a little bit exercise here. I think we learned through exercise. So let's look at some example here. These equations are called large signal equations. Large signal equations are usually used to solve DC bias problem. So whenever we solve DC problems, we should use these large signal equations. Thursday, we will talk about small signal equivalent circuit. That's after we find the bias, we use a small signal equivalent circuit. So let's look at example we have discussed so far. So if we have a resistor, okay, and we have an NMOS transistor here and ground, well, we often write the power supply to be VDD because it's kind of ultimately connected to the drain. So VDD is kind of a commonly used symbol. The resistor connected to drain, sometimes we just commonly call that RD. You can name it anything, but these are the common practice. For this example, we just assume we apply a bias directly to the gate. So let's look at simple numerical examples. Let's say VDD is equal to 3 volt, okay? RD is 1 kilo ohm, okay? And for this transistor, we often label transistor by M. M stands for, obviously, MOSFET. So if you have more than one transistor, then it's M1. You just label them sequentially, M1, M2, and so on. So here we have just one transistor, so it's M1. And we can assume Kn. That's the parameter for the drain current. Let's say this is equal to 2 milliamp per volt square. So the unit for Kn is amp per volt square. All right, and so let's add, and we need Vt, Vtn. We need the threshold voltage for transistor M1. So these are the M1 transistor parameters. Let's say 1 volt. I'm trying to simplify the numerical calculation here. So we can ask the question. So question 1, for example, if Vg is 0 volt, what regime does this transistor operate in? And what is the drain current? And we can say if this is output Vd, what is Vd here? Okay. So if gate is 0 volt, which mode is the transistor in? Cutoff. So Vg is actually less than Vtn. So this is in the cutoff mode. Okay. Cutoff mode, IDS is equal to 0. Okay. And Vd is equal to VDD minus the current times RD. And since there's no current, so it's simply equal to VDD. All right? Okay. All right, so that's easy. So let's say what happens if we increase it to 1 volt? 1 volt. Which mode is the transistor in now? So Vg is 1 volt. V overdrive is equal to Vg minus Vtn. Okay, so 1 minus 1 is 0 volt. So it's just on the verge of turning on, so still off. And the current is still 0, so ID is still 0. So Vd is still equal to VDD. But it's on the verge of conducting current, okay? So this is almost trivial. So next question is, well, we increase that to 2 volt. Okay, 2 volt, what happened? 2 volt, okay, the transistor turns on. It's greater than threshold, so it turns on. We don't know whether the transistor is in saturation or triode. So the solution process is always two-step process. We assume, okay, so we assume the transistor is in, M1 is in saturation. Usually, you can roughly guess whether the transistor is in saturation or not. So if you are, just a little bit above threshold, it's probably in saturation mode. The algebra for saturation is a little bit simpler. So you always start with saturation. It's up to you, but if you start with this assumption, it's easier to solve the current. And if your assumption is not correct, you can always go back and do the other algebra. So, okay, in this case, we say ID is equal to 1/2 Kn times really V overdrive square. So V overdrive square. And V overdrive is 2 minus 1. So V overdrive is 2 minus 1. So that's 1 volt. Okay. So this is equal to 1 milliamp because Kn is 2. So you see why the units of Kn is amp per volt. So here we give it the numerical value of 2 milliamp per volt. So it turns out to be 1 milliamp. And in this case, Vd is equal to Vdd minus ID Rd, okay? And this is 1 milliamp, 1 kilo ohm, so this is 1 volt. This is 3 volt. 3 volt minus 1 volt, that's equal to 2 volt. Here, Vd is also equal to Vds, okay? And Vds is greater than V overdrive, which is 1 volt. And so the assumption check. So this is okay, that's correct. And this is our correct answer. Your output voltage is 2 volt, okay? So if we kind of plot our transfer curve, we plot our Vg here, Vd here. So we say 0 volt, it is 3 volts. And 1 volt is also 3 volts. And 2 volt, now it's dropping to 2 volt here, okay? So Vd starts to drop. And we can continue asking the next question. Okay, what happened when Vg goes up to 3 volt? Okay, 3 volt, the overdrive voltage, V overdrive is now 3 minus 1, so this is 2 volt. Okay, now we don't know. Let's say we guess M1 in saturation, so this is still assumption, okay? So our assumption is M1 is saturation. All right, and we calculate ID. ID in this case is simple. So 1/2 Kn now times overdrive square, so it's 2 square. So now this is equal to 4 milliamp. Kn is 2 milliamp, so this is 4 milliamp. 4 milliamp, okay, now we go back to calculate Vd. Vd is now Vdd minus Id times Rd. So now this is 4 milliamp times 1 kilo ohm, that's 4 volt. So this become minus 1 volt, so this is obviously wrong, not physical, right? So this is not physical, okay? Why not physical? Well, the voltage is 3 volt at the top, 0 volt at the bottom. Vd has to be somewhere in between 3 and 0, so it cannot be negative voltage. So that's wrong, okay? And so we therefore say, okay, wrong assumption. So now we do our second assumption, okay? So now we assume M1. Now it's pretty sure, actually you don't need to assume, this is in the trial region, okay? In the trial region, okay, you can still calculate ID, all right? So ID is now Kn V overdrive VDS minus 1/2 VDS square, okay? But VDS is unknown, okay? So what is VDS? VDS is equal to VDD minus ID times RD, okay? So this is equal to 3 volt minus KD is equal to 1 kilo ohm, okay? So I'm going to, I'm doing something kind of a little bit dangerous here. You need to decide whether you want to do this or you want to pursue a safe route. So I'm using milliamp for all currents, for all I's, and using kilo ohm for all R's. So I have to remember when I solve my current, I'm actually solving it in milliamp units. You don't have to do that. You can just put I in and put 1,000 into the RD. You will solve your I, which will be in terms of amp. And numerically, they should be the same. I'm just trying to simplify my number calculation here. Okay, so now you see I start to have a little bit more complicated equation. You substitute this into VDS, okay? And remember Kn is 2, so you have ID equal 2 times OV is overdrive voltage is 2 VDS. So VDS is, let me see which one is easier. Actually, maybe yeah, okay, we can solve it this way. So 2 times 3 minus ID, okay, minus 1/2 3 minus ID square, okay, and you solve the current. So now it starts to be a little bit more complicated. This is a second order polynomial equations. So ID equal here 12 minus 2ID minus 9 minus 6ID plus ID squared. Now you need a calculator to solve this. But you can solve ID. So there are 2 values of ID. So there is a value of ID1 and ID2. For polynomial, there are 2 solutions. Usually, one of them will be too large, okay? One of them is too large. How do you know too large? Well, you substitute it back there, you get a negative voltage for VD. So again, that solution is not physical, okay? And one of the solution will actually be acceptable. So you take this smaller current. I don't have a calculator, so I won't calculate it here, but assuming this is a small one, and so this is checked, but you still need to go back and verify that indeed VDS in this case is smaller than VGS minus VTN, okay, or V overdrive. So you need to verify that. Okay. So that's the general solution process. You can apply that to many different examples. Okay. Yep.
One question. For part 3, you drew the graph of VG and VDF. Yeah.
Here.
Is this graph linear or it's not?
This graph
Yes.
is not linear. So, going to 3, actually I solved it earlier. So it drops to 0.7 milliamp, and then it goes down very slowly. So the transfer curve you get is something like that. So it's not linear. And so this is in the trial regime. So somewhere here is a crossover. Here is the transistor is in the trial regime. And here is cut off. So here is saturation, okay, saturation regime. And here it's in the cutoff regime. All right. So saturation here is roughly linear, okay? Roughly linear, meaning it's a straight line. So this is a regime where we will use this bias regime, use this for amplifier. Okay, if you want to design an amplifier, you want it to be in this regime. Now, you say, how do we know it is in this regime? Well, it is your responsibility as a designer to design it to be